Okay, so here we're going to take a look at, in this section, right, this idea of coloring a graph. Right now, we want to think of, here if we think of a map, right, and what we want is in just a general map, we avoid having, in this case, the states to have the same color if they share a border, right? So the question becomes, right, what's the minimum number of colors you would need to have such a coloring, right? So here, the idea here is if we just let's think of the states like to be the vertices, right? So let's just look at kind of like the West Coast here. Like if we had Washington, Oregon, California, and then Nevada, right? So we treat the states, excuse me, like the vertices, and if they share a border, then we treat those as the edges, right? So you have Washington, Oregon, Oregon, California, and then Oregon and California both going to Nevada. Okay? All right. So that's kind of the idea here, right? Now, we can, when we assign, so before this is kind of the extent of our graph that we did, but now what we're going to do is we're going to assign some coloring, right? And so what that means now, here, so you say, all right, so what if, actually, let's use here, here, here. So this is a coloring. Right now, what we want to have is what's called a proper coloring. Here, let's get it here. A proper coloring, right? And this is going to happen where we assign colors, so no adjacent vertices. Vertices have the same color. Okay. All right, so that is what a proper coloring is, right? Now, again, every graph will have a coloring, right? You can just choose a color. So the worst case scenario is that you just use a different color for each vertex, right? And that is a coloring of a graph, right? Now, the more interesting question would be, well, what is the minimum number of colors needed for a proper coloring, right? And that is what we define as the chromatic number. Which we use this notation, right? A Greek letter chi and then G, so the chromatic number of G, right? And this is the minimum number of colors needed for a proper vertex coloring. And again, every graph will have a chromatic number, right? Finding that would be kind of what the problem here would be, right? What that's going to be what we're going to be tasked with doing here, right? Now, just some common graphs that we see, the complete graph, right? So KN here. So the chromatic number, since if we think of this one, right, every vertex is connected to every other vertex, so they're all adjacent to each other, so the chromatic number of a complete graph will always be N. All right? Okay. Now, our bipartite graphs, regardless of whether what K and M is going to be, so K and M, it will always be 2, right? Where bipartite for each set, right? Since there's no circuit in there, right? You can just have the 2 sets of the vertices be a specific color here. And in general, when you see a graph that has a triangle, right? Any graph with a triangle here, whether it's the whole part, the whole graph, or just a subgraph here, then you're going to need at least 3 colors. Okay. All right. So let's take a look at some examples here. Okay, so we'll take a look at this here. Right now, again, I see a triangle here. So we're going to need at minimum 3 colors here. Right, and as it turns out, we are going to be able to do this with 3. Right, and we can see this here. This tool here has a nice here. So it'll assign the coloring and it'll find the chromatic number. Here they call it the color number is 3. Right, and we can see here they're labeled above the vertex numbers, right? How many colors we'll need, right? And that triangle makes it so that we are going to need 3. So the chromatic number here would be 3. All right. And looking at this one, so here we have a complete graph, right? This is K6, right? So we could see that we're going to need 6. The chromatic number here is going to be 6. All right, and indeed here, get graph coloring, and we see we have 6. Right, each one of those vertices is going to be, for a proper coloring, going to need a different color. All right, and then our third example here, right, we see we have a bipartite, right? AC, right, is one set of vertices, and BED are the other set, right? And actually, in general, let me go back to this. This is KM. It doesn't need to be complete, right? So this will work for any bipartite graph. Let me make a correction here. All right, so it doesn't necessarily have to be complete. All right, so here, let's go back here. All right, and then here, graph coloring, and we see here what I mean, where the 2 distinct sets, they can be their own colors, 1 and 2, right? Because in the bipartite, these will never be adjacent, and in this set here will never be adjacent to each other. Okay? All right, so in general here, there are bounds to the coloring. All right, so we could say some bounds. On the chromatic number. Just use the abbreviation here, chi of G. All right, so the lower bound, all right, chi of G is going to be bigger than or equal to the size of the largest complete subgraph. Okay, and what that means, if you see a triangle, right, that is a complete subgraph there, so we need at least 3, right? And if you have a square, but not just a square here, but a square, so sorry, not a square, a triangle, right, with a 4th vertex connected here, right? So here, like here, so if you had something like this, right, minimum 3, but then if we have within here right? Then we need minimum 4 there. So that's kind of the lower bound. Right now, the upper bound for the chromatic number G, right? That's going to be less than or equal to the max degree plus 1. Right, so whatever the maximum degree, and then you add 1 to that. Okay? Now, excuse me. The max, at least, is a bit of a loose bound, and we aim to have a better upper bound. Okay? And that's what we'll focus on next. Right? In our next video, we'll look at something called the four-color theorem and Brooks's theorem to determine chromatic numbers. All right, but here we just get a general idea of what we're looking at here.